Sure. Anyway, so I'm going to talk to you about a bunch of different techniques, right? So they are mostly taken from this book, Mining of Massive Data Sets, right? So the first thing I'm going to talk about is something called locality sensitive hashing. Okay. So people are familiar with the hashing, right? People are familiar with the idea of hashing, right? So what has happened over the years is that a lot of these, large data handling algorithms, right, have been increasingly relying on some form of hashing or the other to make the computation and everything scalable. Right. So this is there are many things that you will see now that are actually implemented and in use in real systems that rely on hashing. Right. So typically, for most of these algorithms that we will see, you give up correctness. Right. You give up perfect correctness. Right. You are happy to accept probabilistic guarantees of correctness so that you can run things in a tractable time. Right. So that's typically what you will see for the 3-4 algorithms that I will talk about, right. So this idea of locality sensitive hashing has a lot of applications. So here is one motivating example. Oops. Okay. Let's say that you are given an image like this, right. So you took a picture. There is some occlusion here, right. So you would really like to see how this thing will look like without this occlusion. So you want to go to this database of millions and millions and millions of images out there, try to retrieve some 10 images that are very similar to how this image will look like without the occlusion, and then perhaps recreate a full image that's as close as possible to the original thing, right. So the problem here is that, when I give you an image like this, right, how can you go to such a large database, right, like millions of images that are there on the web. So here is an example of retrieving 10 of the nearest neighbors, right, from a collection of 2 million images. Right. So just think about the kind of computation that is going to be involved, right. So you have to compare 2 images, right, and you are going to do this over 2 million such data that's available, and comparing each image itself is going to take some time, right. So all of this is fine. This given a one query image and retrieving this is all fine, but suppose I want to do this in a production system where people are going to come and keep firing queries to me, at the rate of a few thousand a minute, right. Imagine the amount of computation that I have to do, right, if I'm going to do this in a pixel by pixel comparison of all the 2 million images and so on and so forth. So what we really want is some kind of a cheap way of recovering the right image, right. So it turns out that a lot of problems that we would like to solve can be expressed as finding these kinds of similar sets, right. So what we call as finding near neighbors, right, in a high dimensional space. Right. So for example, one use case that I'm going to take and delve a little bit in depth is one of finding duplicates in text documents, right. So why is this useful? So if there could be web pages that are copied from one another. Now let's say I'm building a news aggregator website. I would like to pull in all these web pages and show those stories which are essentially the same story, maybe shown slightly differently, maybe with a couple of paragraphs deleted or a paragraph inserted here and there, but I would like to kind of group all of them together and show you just one link for this, right. You don't want to see the top 10 hits when you search for a news story, basically the same Reuters news story published in Times, Hindu, right. So everything, you don't want to see that. So you want to see only one copy of a story, right, and all the others collapse underneath it, saying, yeah, this is the same story, there are multiple of these, right. So this is an actual use case that people have, right. Now the question is I'm not just looking at retrieving one image and 10 similar images, right. I'm going to looking at the entire 2 million document database. I'm going to do pairwise comparison to find similarity here. Right. So you can imagine the amount of computation that might take, right. And likewise, if you have gone to Amazon or any of the other sites there, right, let's say customers who bought this also bought, or similar customers, right, did this, or similar products and so on and so forth, right. How do they get these similarities? They basically have to compare. So people have come to the website and they have, somebody like Amazon, right, probably has a few million customers who are buying things on the Amazon website, right? And they are buying over, a couple of million product inventory that Amazon has, right? And now I'm saying, okay, people who are like you bought these also, right? So just, I mean, it may just look like a simple feature that shows up on the Amazon web page when you reach there, but imagine the amount of computation that had to go on behind the scenes to figure out who are the similar purchasers, right? Likewise, we have, I just showed you an example with images and so on and so forth. There are many ways in which this kind of near neighbor search kind of manifests itself. If you actually go to the book, I think they have something like 10, 12 use cases where near neighbor search is something that we have to solve, right? So, the goal here, what we are going to talk about today is given a high dimensional data point or given a collection of these high dimensional data points, right? So, you can think of an image as just a long vector of pixels, or a document as a very, very long vector of words present or absent and so on and so forth, right? And some distance function that tells you how far away x1 is from x2, or how similar x1 and x2 are, if you want to take the inverse of that, right? Okay. Sorry about that. I'm still figuring out how hard to press these buttons. I'll eventually do that. This is, so you're going to see the formalization of this approach in a couple of days, right? So this kind of trial and error learning. But anyway, going back, so yeah, so I opted not to teach reinforcement learning for a change. So somebody else will do that. So the goal is to find all pairs of data points xi, xj that are within some distance threshold, right? So you're also given a threshold, you're given some threshold, yes. So you want to find all pairs of points x and j, xi, xj, right, that are within a threshold distance of each other. So that's the problem statement we have, and obviously the naive solution is going to take order of n squared, right? And but you're going to say that it can be done in order of n. So what we are going to give up is the guarantee that I will retrieve all points that are within the threshold, all pairs of points that are within the threshold. But what we will end up with is an approach that says that if a pair of points are close enough, then with a very high probability you will recover them, right? And if a pair of points are far enough, right, with a very high probability you will reject that pair as a candidate pair, right? So this is basically the guarantee that we are going to give, right? If they are close, right, if less than the threshold distance, with a very high probability I will retrieve that pair. If they are very far away, right, with a very high probability I will reject the pair. Now I will not give it back to you. Right? There could be false negatives, there could be false positives. So we are not eliminating all of that, but what is the thing that I give you is something that can run much more efficiently than order of n square, right? So what we are calling now this problem is we are going to find near neighbors in a high dimensional space, right? And so for the first application that we'll look at least for the pre-lunch session, right? So I'll just stick with the Jaccard distance or the Jaccard similarity. So how many of you are familiar with Jaccard similarity? One? All of you? Okay, now I'll have to start doing what I do with my normal classroom. How many of you are not familiar with Jaccard similarity? Oh God, okay, actually your arms work, is it? So usually I have this problem that my class that nobody puts their hand up for anything, right? So I start phrasing the questions so that I get the answer I want. But unfortunately you guys are actually answering. So the Jaccard similarity is a similarity measure between two sets, okay? And you can see what it is, it's intersection over union is what they call. So C1, C2, so I look at the cardinality of the intersection between C1, C2 divided by the cardinality of the union. So, and this is a similarity measure. So if I want to make it a distance, I basically do 1 minus that, right? So if C1, if you look at the distance between C1 and C1, it will be 0, right? And it actually you can verify that it satisfies all the other properties of a distance, right? So it satisfies the triangle inequality and etc., etc., etc. So it's a most popular way of measuring distance between sets, right? And if you think about it, many of the applications I was telling you can actually be thought of as sets, right? For if you take the example of customers who bought this also bought this. That's obviously a set, right? I mean, when you buy something, it's a set of items that you buy, right? But also when I'm talking about duplicates of documents, I can also think of those as sets, right? So each word appearing in it is a collection of words, right? I can think of it as a collection of words, and so even if a few things, some things are missing here and there, or words or orders or interchange and things like that, I would still like to consider them as being equivalent, right? So I can think of those as sets. So that's the first thing that we look at. So similarity measure between sets. Okay, I don't know how many clicks went forward, but I'm assuming this is good enough, right? So again, getting back, so given a large number of documents, right, where the number of documents can run into millions or billions, I want to find near duplicate pairs. Okay, so that's basically the idea here. And like we said, right, I want to detect which websites are actually mirror sites. Sometimes sites could be official mirrors, sometimes they are unofficial mirrors. And so if I am maintaining a site, I would like to know if somebody else is unofficially mirroring me, right? Wow, okay. And or if I'm searching and indexing a website, if it's a mirror website, I really don't have to search, index it all over again. I can just use whatever I have done earlier, right? So that's a couple of applications that we already talked about, right? So there are many problems, right? So I can interchange paragraphs when I'm actually going from one document to the other, right? Or I might actually leave out a few sentences altogether, right? And then, so typically if you look at news stories that are put out, right, most publications take the first 3 or 4 paragraphs, they have a cutoff. The story itself might be 7 paragraphs long, but they will just pick some 3 or 4 paragraphs because they have some word limits on what they can produce, right? So these kinds of things can happen, but we will still like to consider them as near duplicates. So even if there are only 4 paragraphs that are matching, if they are matching exactly, right, we would like to consider them as near duplicates. Of course, being in academia, so there is another instance of near duplicates that we would like to catch. Plagiarism, right? So you might change a few words here and there, but we would still like to catch those kinds of things, right? So that's the first problem. So we would like to come up with approximate notion of similarity. So that is nothing to do with locality sensitive hashing. In fact, it's basically addressed by the way we represent the document. So I'll come to that in a bit. Then the second part is there are just too many documents to compare all pairs. Right? I can't do that in a conventional manner. We already talked about that, order of n squared, right? And in fact, the documents are so large. If I really want to do this billion versus billion comparison, even if I don't care about the time, the memory might be prohibitively expensive. So I might have to put everything on disk and then read a bit into the memory at a time and then start doing the comparison. And if people have ever tried implementing things with lot of disk access, so you know that it's just not going to scale, right? So we have to worry about. So we're going to talk about this in a 3-step process, right? So let's catch up because I've been playing around with the mouse pointer, right? So the first thing is we are going to look at a way of representing the documents, right? It's a form called shingling, right? So I will talk about shingling, even though it's very peculiar to document representation. So it can be used in a few other domains, but it's a very powerful idea for representing documents for some of the things that we will look at, especially these kinds of near duplicate searches and so on and so forth, right? And the second thing we'll talk about is something called min hashing, right? So it's a mechanism for converting very large sets, right, into short signatures, right? And we'll make a formal what we mean by signature here. We'll convert a very large set to short signatures, right, while we measure some notion of similarity, right? Basically the idea that we want to figure out is, hey, if 2 sets have the same hash value under min hashing, right, the probability that 2 sets will have the same hash value under min hashing is equal to the similarity between the 2 documents. So more similar the 2 documents are, the more probable that they will have the same hash value, right? And the less similar the two documents are, the probability that their hash values will be same is very small. Okay, so that's basically what we want to show. Some notion of similarity that we preserve with this signature, and then we go to this locality sensitive hashing, which allows us to identify candidate pairs very quickly, right, with arbitrary levels of guarantees that we want, right. So min hashing is a very weak notion of locality sensitive hashing. So we actually take that and we will then come up with a technique to amplify it. So the next lecture, which is in the afternoon, I will start looking at making this more formal, more generic, right, not just focused on min hashing and this, right. Okay, good, that didn't work. So the overall flow is as follows. So the document, I am going to take that, I am going to shingle it, right, and then I will get a set of strings of length k that appear in the document, right, and then I will min hash it, right. I am going to get a set of signatures. So we have short vectors that represent the set. That is what the min hash gives you, right, these signatures, right. And then we kind of amplify these signatures and we do locality sensitive hashing, and then we get candidate pairs. So the thing with the way we are going to do this is that what I return to you could have a lot of false positives. I might return pairs of documents, right, which are not similar, but it will be a much smaller fraction than the n squared pairs that I would have to check, right. So I will return candidate pairs, and then you have to do an explicit check if you are not tolerant to false positives. If it is okay that you can tolerate some small fraction, say 3% of false positives or 4% of false positives you can tolerate in your answer, then fine, you can just keep it as it is. But if you don't want, you want 0 false positives, right. If I say these two are similar, then I want to make sure they are similar, then you basically run your actual similarity checking algorithm of this, right. So we will start with shingling, right. So there are many ways in which you can convert a document into a set, right. So the most popular of these, right, is called bag of words, right. So have people come across this phrase bag of words? Okay, 2, 3, 4, yeah. So the idea is that I am going to take all the words that appear in the document, not worry about the order in which they appear, right, and then I am going to say, okay, the document is just this bag of words. So that is basically a set representation, right. You can even think of the way you represent this is like some kind of a characteristic function, right. So for every word you will have an entry there, and if that word appears in the document it will have a 1, if it does not appear it will have a 0, right. You can think of this as a vector in that case, you can also think of it as a set representation, right. So the bag of words is the most popular, right, and the second one is sometimes what people call the set of important words, right. So I do not know if people have come across this notion of stop words, right, things like the, is, etc., right. No, etc. is just etc., not an example of a stop word, okay. So these are stop words, these are kind of not really content words. Sorry? How did that happen? Maybe I tapped with my pencil. There you go. I shouldn't say dot. Huh? Anyway, it's too young a population. They have not even seen Indra. Anyway, but going back, so using these kinds of bag of words appearing, even if I throw out all the common words, even if I keep only the the content words, right, and I try to represent this as a set, it turns out for this duplicate problem it's not quite enough. Why? I am actually trying to find duplicates, right, but I might use the same words and write a very different article about the topic, right. So if I start looking for similarity in the sense of or these words appearing across these two, then maybe I'll probably get documents that are on the same topic, but not necessarily duplicates. Get that? So I really need a different way of accounting for order in the words, right? Bag of words completely dismisses orders. I want to somehow make sure I keep the order, but I still make it into a set, right? So that is where people came up with this idea of using shingles, right? So a shingle, right, is what sometimes called a k-gram, right? So people typically might have heard of the phrase n-gram, which is the same. It's basically a sequence of tokens, right, that appear in the document. So it could be characters, could be just character tokens, could be word tokens, right, or whatever else you want, right, depending on what application you are looking at. I mean, if you want, you can even try to shingle an image. Right? It could just be a sequence of pixels and things like that, right. So here is an example. So the document is ABCAB, right, and I want to get the set of two shingles in this document, right, and so I get AB, BC, CA, then I get AB again, but I already put that in, right. So I don't count the shingle twice, right. So that's the basic representation. Of course, you can, there's nothing written in stone, right. You can come up with an algorithm where you treat the shingles as a actual bag, right, as opposed to a set, right. So if it's a set, then I won't repeat AB. If it is a bag, then I will repeat AB twice. I mean, this has different implications for what will be the how I count similarity and so on and so forth. But for the time being, let's just assume that we stick with this, right. So no, it's a set, right. Very short, I mean, this is okay for illustration purposes, but a very short shingle, right, is not very useful. Why? Because literally it's saying every pair of characters. I mean, you are going to find every pair of characters in every document, right. It's not like, it's not a very discriminative representation. So typically people actually look at much longer shingles. They talk about shingles of length 9 or 15. So it's like 9 characters or 15 characters and so on and so forth. And instead of looking at the entire document and doing this comparison, right, we can do this with short strings, right. Here's another example. Here where we assume the tokens are words, and you can see the sky is blue and the sun is bright, gets translated to so many different 3 shingles, right. So if I'm going to have much longer shingles, like 9 characters or 9 word shingles or 15 word shingles and so on and so forth, just imagine the number of possible shingles that I could have, right. So let's just assume regular text, right. So you have 26 characters, and then you have some punctuation, special characters and so on and so forth. You have space and all of that, and if I say I'm going to look at a 15 shingle of characters, it's actually your alphabet size time to the power 15, right. Those are the set of possible shingles that you're going to have, right. That's a very large number of shingles. So you don't want to actually keep all of that in memory at any one of time. So what you're going to do is, as and when you construct the shingle, right, I'm going to hash it into a bucket. Okay, make sense? As soon as I construct the shingle, as I keep reading, okay, this sequence of characters, let me compute some hash function, put it into some bucket, right. Now what I'm going to do, I'll just count the buckets, right. So if 2 documents are similar, if all their shingles hash into the same set of buckets, right. Again, you see the power of hashing is I really don't have to represent all my shingles and count them, right. All I need to do is, like they say here, use a 4-byte target value, right, hash value, and then you can maintain that in memory, right. You don't have to worry about the actual shingle itself, right. But the problem is multiple shingles might hash to the same value, same bucket. So there's a small chance that you miscount the number of shingles, the occurrences of a shingle, right. the idea is that you choose such a large number of buckets, right? And it's not that every possible combination of shingles that we are talking about, right? So whatever I was telling you, right? 26 power 9 or 35 power 9, all of those combinations are not going to happen, right? In reality, only a small number of those combinations will actually occur, and therefore, if you keep a large enough number of buckets for you to hash them into, right, the probability that you will miscount the shingles is very small, right? But it's not zero, but it's very, very small. So we actually don't talk about it, right? So we just assume that it's such a small probability event that we don't have to account for it. Okay. Okay, let's move on. So now what happens? I have taken a document D, right, and I have converted that into the shingle representation, right. So once I have this as a shingle, remember I was saying that we'll treat shingles, the shingle representation as a set, right. Now the notion of similarity between documents, now I am going to use is the Jaccard similarity or Jaccard distance, right, whichever way I want to look at it, right. So this is what I was telling earlier. So if a document has a lot of shingles in common, because you are actually looking at the shingles as sequences that could span multiple words with the tokens and things like that. So even if the shingles are out of order, right, even if the text things are out of order, a lot of shingles will show up in common between the two documents, right. So that's so this makes it robust to people rearranging sentences, dropping a few sentences and so on and so forth. It makes it robust to that, and it also makes it robust to the problem that I was telling you with the bag of words, because this actually has a notion of sequence. So and so these are all things that come from practice, right. So how large the shingle. So for example, people have actually done some analysis on documents of the length of a typical email, right, and show that if you have shingles of size 5, this is 5 words, right, shingles of size 5, right, they are okay for a typical email length documents, right. But when you're talking about news stories and other kinds of articles and so on and so forth, then they want to have a larger k. So k equal to 9, which is the most common implementation, but k equal to 10 is also better for these kinds of longer documents, right. By long documents, I mean typical articles, news stories, and so on and so forth. As emails are a few sentences long. Yeah. Right. Yeah, this is again, like I said, I'm shamelessly stole their slides, so I don't want to say their slides are not good, but yeah, they're kind of belaboring some of the most obvious points again and again. But I really like this comparison argument that they have given here, right. So the time they assume is 1 microsecond per comparison, right, and then they say that this will actually take you 10 power 6 comparisons per second, right. So that means 1 microsecond per comparison. It will still take you 5 days just to compute this pairwise Jaccard similarity for a collection of documents. So this is not something that you want to do, right. You want to compute this and then do something on top of it. So you don't want to spend 5 days just computing the similarity, right. And yeah, the larger it becomes, it just goes faster and faster. So now what we will do is look at okay, now that we have shingling, is there a way to make things more efficient, right. So that's basically what we're going to do. Yeah, so this we already should I talk about encoding sets as bit vectors? That's just using the characteristic of the set, right. So I have a function that give you a 1 if the element belongs to the set, gives you a 0 if it doesn't belong to the set, right. So what I can do is, let me see if the matrix comes up. Yeah, good. So I can represent a collection of documents by this kind of a 1-0 matrix. Okay. So what does this matrix do? So the columns are documents, right, and the rows are shingles, right. If a shingle is in a document, then I'll have a 1 there. If it's not there in the document, I'll have a 0. So so the first document has shingles 1, 2, whatever, 5, 6, and 7, right. So to read the document, you read down the column. Okay. So this is the representation. So typically we never represent this matrix ever in memory. Why? it will be mostly zeros, correct? It will be mostly zeros, and there will be some other form in which this data is already represented, right? So we don't want to do this the full representation again. So for example, we're talking about sets of products and items that customers have purchased, right? Then the item cross customer thing would be there in some database, some DBMS store already in your system, right? So you don't want to kind of read the DBMS store and again create a matrix or anything like that. So typically this matrix is I'm using just for illustration purposes. Just remember that you will never actually construct this matrix, right? So yeah. So can you tell me what's the similarity of C1, C2? Once you have this, it's basically take the two columns corresponding to those, take an intersection and take the union of the two columns, and then you get the similarity. Okay. Right. So now what we have done, so instead of a shingle being represented by the actual the set of characters or set of words, we have kind of converted that entire thing into some kind of a Boolean matrix. Right? So the Boolean matrix is kind of easy to represent in memory. So it's you think that we are getting somewhere, right? But we want to make it even shorter. We don't want to maintain that full matrix in memory. So we want to make that even shorter, right? So what we are going to do is somehow find a summary of each of these columns, right? And once you have the summary, I should be able to compare these summaries and tell you which columns are similar. Okay, this is the goal that we want. So I want to come up with a summary of these columns. So I don't want to represent the entire set of shingles, right? Because the number of shingles, as we know, can become very large. So I don't want to represent all the rows, right? The columns have to be represented, but that binary matrix, I want to make sure that I have a lot fewer rows than the number of shingles. So it's a kind of a compressed representation of the document, right? And this compressed representation should be such that I can look at this representation and tell you if two documents are similar or not. Okay, I shouldn't lose that notion of similarity when I do this compression. Okay. Right. So what we are going to do is we'll introduce a hash function, right? We'll introduce a hash function that allows me to reduce the representation to a small signature, and if two signatures are quote unquote similar in some way, right, then the documents C1 and C2 are also similar. Okay, so that's basically what we are shooting for. Yeah, let's just forget about the second half of the previous slide. Okay, let's go from here. So the idea here again is that then if similarity of C1 and C2 is high, then with a very high probability I want the hash value of C1 equal to hash value of C2, and similarity of C1 C2 is low, then with a high probability we want hash value of C1 not equal to hash value of C2. So this is a guarantee that we are going to give, right? So so this whole idea of this min hashing and all this locality sensitive hashing, it all depends very much on the notion of distance that you are using. Not all notions of distance support a locality sensitive hashing family, right? Luckily for us, a lot of the more popular notions of distance actually support this, right? So Jacquard is one, and then we'll talk about cosine distance later. Cosine has a equivalent sorry? Yeah, cosine similarity. You can convert that into a distance, just like you do Jacquard similarity into a distance. You can convert cosine similarity into a distance. That has a hashing family associated with that. And then L2, right, has a hashing family associated with that, even though it's not quite very robust, right? So I'll not really get into the details of L2's thing. And likewise, you can have Hamming distance. Hamming distance supports notion of locality sensitive hashing and so on and so forth, right? So it's a very, I mean, you can come up with, there's a lot of papers that have been published on different kinds of distance measures and an equivalent locality sensitive hashing function for that. So we'll assume that you have a suitable hash function, right, and the one suitable hash function for Jaccard similarity is actually what we call min hashing, right. So the idea behind min hashing is fairly simple actually, okay. So think of your matrix that you had, right, that 0 1 matrix that I was talking about, right. So you had a bunch of shingles and you had a bunch of documents, right. Now assume that I randomly permute the rows of that matrix, right, I randomly permute the rows of the matrix, then the hash value of each of the columns, right, because each column is a document, right, I have to hash each of them. The hash value of each of those columns is the first index at which I get a 1 in that column. Remember, it is a sparse matrix, right. So at any random permutation, the high probability there will be a string of zeros at the beginning, right. So the hash value for a column is the smallest index at which I get a 1, right, under that permutation. So for every possible permutation I have a corresponding hash function. So the hash of C under permutation pi, right. So the hash of C, which is some column under permutation pi, is the minimum index such that there is a 1 there. Okay. So let us take an example here. This is some permutation of that input matrix, right. So this, okay, yeah, that is a permutation of the input matrix. So what does this mean? So basically, I always forget the notation here. I think so. 2 comes to the first one, right, and so on and so forth, right. So 1 goes here, and row 2 comes there, and etc., right. So you can see what the permutation is. Let me write out the permutation. Okay, so this is not what it is, right. So the permutation is the following. So the first row goes to the second row, right. So that means I get a 1 here, right, and the second row goes to the third row, so I get a 1 here. This goes to the 7th, right, so I get a 0 here, right. This goes to 6th, so I get a 0 here. This goes to 1, so I get a 0 here. This goes to 5, so I get a 1 here. This goes to 4, I get a 1 here. Okay. So this is the permutation of the first column under this permutation pi, right. So the hash of the first column will be 2. So that is basically what we have here, right. And does this erase if I press? Okay. Now I become a little scared to try this thing. I press that and suddenly everything goes blank, right, and with my luck the projector might go up in flames, I do not know. So today, so I just wanted to make sure I am not doing anything crazy. So let us do the same permutation for the second column now, right. So what happens in the second column, right. So this goes to 2, so that is there. This goes to 3, so that will be a 0. This goes to 7, this goes to 6, this goes to 1, and the other 2 are zeros anyway, right. So this is my permutation of the second column, and what is the hash of the second column then? 1. So that is what we have, right. And likewise you can look at it, and then you can look at, okay, I can actually do a little trick here, right. So 1 is basically 0, 2 is 1, so the second column is 2, right. The third column hash is also 2, and the fourth column hash, okay, so what goes into row 1 is 1, so therefore it will be 1, right. So this is basically the signature, right. Okay. So I have taken this matrix, right, and I used one permutation, and then I have converted that into a signature, which is just a single row, right. And of course this is not going to tell me anything, right. I can still say that 2 rows are equal, right. Okay. Here is another permutation that we can look at. Okay. and I'm not going to walk you through this, but you guys can look at it, right? I'll leave you there to stare at it and convince yourself that that's the right permutation, right? That's the right signature matrix, right? Likewise, I have the final signatures. I can do that, right? So basically, I have this. Right? So I mean, this is the typical way in which we store the index, but you can also think of storing it the flip way, right? So what is the element that came into the first row to give you the 1? So that's basically what it is, right? So you can store the row indexes. Let's not worry about that, right? I'll skip that part now, right? So let us say that I choose some random permutation pi. So my claim is the following: the probability that h pi c1 equal to h pi c2 is equal to the similarity of c1 and c2 for some arbitrary permutation pi. Okay, seems slightly counterintuitive as to why are we relating these two things, right? So